Okay, I'm going to go through some what I'm going to call spinning bucket examples here. And this will help you with the last two questions that are on that circular motion list. So let's say we've got a bucket and we have a little, I don't know, we've got a little creature in the bottom of the bucket. I'll just draw a blob with eyes. Okay. And he's being spun around in a circle. So we're thinking about the forces acting on him. We're not going to think about the bucket. That would be tension. We're not going to, that's not our focus here. Our focus here is the item that's inside the bucket. Okay, so he's going to spin around in a circular motion with a radius. So we're going to think about what happens with him at at the top and the bottom of the circular path. Okay. All right. So let's talk about the bottom first. Okay. So what are the forces acting on him when he's at the bottom of the circular path? So just imagine me in our classroom whirling a bucket around on a string, and it's at the bottom part of the circular path. Okay. So at this point, he's got a force of gravity pointing downwards on him. He's got a normal force pointing upwards from the bucket, from the bottom of the bucket. And we said that here, our normal force is going to be greater. That's why you have this feeling of being heavier if you were him in the bucket. You were being swung around the bottom part of this path. Okay. Um, the way we would set our F net equals mass times acceleration up here, we would have normal force minus force of gravity. I'm going to go ahead and call that m times g because we know that's what that is. And that equals our mass times v squared over r. Okay. So remember, this is our vector sum of our forces. This is our mass times acceleration. And when we're in centripetal motion, we've got this centripetal acceleration of v squared over r. Okay. And this is what tells us normal force has got to be greater than force of gravity. Our net is what force is pointing towards the center of the circle. So we've got a larger force when we do net normal force minus force of gravity, that the balance of that is pointing towards the center of the circle. That's always where your net force, when you're in circular motion, points. Okay. So let's keep going. So you could put in other values here if you needed to. This for this type of problem, the most likely thing you'd be solving for is what's his normal force at the bottom of the bucket, and so you would solve for normal force. You'd have mv squared over r plus m times g. And you're usually given mass, you're given radius. Velocity, we're gonna get to that one in just a minute. Okay. G we know is our 9.8. All right, so let's think about what's happening if we're at the top of the bucket or the top of the circular path. Okay. At this point, it looks a little weird. We've got a normal force that's pointing, it's really pointing downwards because we're perpendicular to the surface that we're on, and that's where our surface is the bottom of the bucket. So perpendicular to that is pointing towards the center of the circle. Force of gravity, again, still pointing downwards because it's always pointing downwards. So here our F net is normal plus force of gravity equals mv squared over r. We can use this part of the path to help us figure out some information about velocity, because we know that we've got to keep a minimum velocity or a minimum speed, a velocity value, in order for us to stay in that circular motion. We've seen that demonstrated in class a couple of different ways, particularly the cup filled with water. So the way that we calculate our minimum, so this is going to be our minimum speed to keep contact with the surface. Okay, so if your normal force is, if you don't have contact with your surface, that means your normal force is 0. Okay, so if we pretend that we've lost contact, our normal force is 0, then we're left with our force of gravity equals our net force, that, or m times a. That means we're in free fall, really. So if we solve for velocity, we can cancel mass because it's on both sides. We've got g equals v squared over r. I'm going to move this r over. So I've got g times r equals v squared. And so then velocity is the square root of g times r. We've got to be at least at this value or above it in order to stay in that circular motion. Okay. And we saw this equation before. Oops, sorry, you can't see that. We saw this equation before when we were looking at orbits. We were talking about a satellite or a space station, something orbiting a large object. It's got to have at least the speed in order to stay in that orbit. Okay. So let's put a few numbers in here. Okay, so let's say that we've got an object that's got a mass of 0.8 kilograms. Hang on, let me make sure that goes with my example so I'm not. Well, let's say 0.08. I'm using an example here and I want to try and match numbers. We got a small object, okay? Just a little blob creature has a mass of 0.08 kilograms. Let's say our radius of our circular path is 1.2 meters, okay? So we can go ahead and calculate what our minimum velocity's got to be, because all we need for that is g and the radius. So I'm going to do the square root of 9.8 times 1.2 gives me 3.4. I got to be at least 3.4 meters per second in order to keep contact with the surface so that I'm not falling out. Okay. I can use that velocity if I wanted to get the normal force, okay, at these different points. I could go back and calculate that. So normal force here, let's see, I've got my mass of 0.08. I'm going to use this 3.4 squared. My radius is 1.2, and then I add that to 0.08 times 9.8. Oops, I'm running out of room there. So let's see what I get there. 0.08 times 3.4 squared equals, divide that by 1.2, gives me 0.77. And then I'm going to add that to 0.08 times 9.8. So that gives me 1.5 newtons, I guess. So that's my normal force on me at the bottom of the circular path. And that's greater than my force of gravity, which would be like 0.78. And then if I wanted my normal force at the top, okay, let's see. The example they gave has got a greater speed than this minimum speed. So let's say at the top we're traveling at 7 meters per second. What's our normal force? I'm going to use this equation. Okay. So here my normal force is mv squared over r minus mg. Just solving for normal force there. Let's see, that's 0.08 times 7 squared divided by 1.2 minus, I think that was 0.78 when I multiplied mass times g. So that gives me a normal force of about 2.5 at the top. And remember, at the top, both your forces, your normal and your force of gravity, are pointing in the same direction. Okay, they're not necessarily equal to each other because they're not balancing each other. They're just direction-wise, they're both pointing towards the center of the circle, and then they're both contributing to that centripetal force that's occurring. Okay, so that should give you some things to help you out with those last couple of questions that are in the assessment.